Hi guys, and welcome to another past paper work through. This is from the Cambridge International AS and A levels papers from earlier this year, and it's Pure Maths paper 2. Now on the instruction sheet we see here we have to give non-numerical answers corrected 3 significant figures or 1 decimal place for angles that are in degrees, unless something else is specified in the question. And in the description below there will be a link to the website where you can download all these past papers from Cambridge, also the marking schemes and some examiners reports, and there will also be in the description timestamps for each question. So if you had a look through the questions and there's a specific one you want to see worked through, then you can just skip to that from the description below. Okay, let's jump in. Now our first question here, we see we have 2 absolute value terms and we need to solve for x. So my favorite way to do this is to get rid of all the absolute value ideas, the negative and positive differences, by just squaring both sides. So I'm going to say, ooh, that's not right. So I'm going to say, take the left-hand side, 5x minus 2, and square it, and also the same on the right-hand side, 4x plus 9, and we square that. So the squaring, because the square of any number is always positive, that gets rid of all the negative ideas here. Okay, now there are different ways to do that. You can also just use one side and change the other one to negative and a positive version and solve it from there. So if you prefer that, go ahead and do that, but this is my favorite way of solving it. Okay, so squaring the left hand side, that gets us to 25x squared minus 10x, so that's minus 20x, and then plus 4. On the right hand side, we've got 16x squared, 9 times 4 is 36, and another one is 72, so plus 72x, and then plus 81. Now this is a quadratic trinomial, so let's get all the terms on one side and 0 on the other. The 25 minus 16 will give us 9x squared, and then negative 20x minus 72 is going to be minus 92x, and then 4 minus 81 is negative 77, so equals 0. Now from here we can either factorize or do completing the square, or we can use our quadratic formula. And for this one, I mean, the numbers look quite big, so I think the quickest way here is just to use the quadratic formula. I'm going to say x equals negative b, so I'm just going to write the whole thing out first, so negative 92. Let me actually do that so we can see the negative better. So negative b plus or minus square root of b squared minus 4 times a times c. All of that over 2 times a. Okay, and then we can just type that in our calculator. So let me get a calculator for us here. Okay, so at the top we have negative 92, so that's just 92. I'm going to start with the plus square root of, and then 92 squared, minus 4 times a times c. Okay, so all of that over, wait, another one, like that. Okay, all of that over 2 times 9, which is 18. Okay, so that gives us 11 if we use the plus, so x equals 11, or x equals, and now let's just change the plus into a minus. Oops. And that gives us negative 0.7 recurring, so that's negative 7 over 9. Negative 7 over 9. Okay, so this shows us it should have been able to be factorized. So that would have been, if we factorized this then, it would have been, what is this? 9x plus 7. And this one, 9x plus 7. And this one would have been x minus 11. So you could have also factorized it into that. All right. And now since it was an absolute value question, we usually want to check both answers to make sure that both of them do work. Okay, so I'm going to let you do that. This is basically the answers. If you have absolute value things, if you have square roots, or if you had logarithms, basically with all of those, you want to check both your answer or all your answers to see if all of them are valid. And now in this case, just looking at it quickly, let's just do a rough calculation just to see if both look like they work. So it's going to be 53 here. It's going to be 53 here, so that's fine. Negative 7 over 9. So it's going to be negative 35 over 9 minus 18 over 9. Okay, so what does that give us? 23, 17 over 9, something like that. And this gives us, well, let's test this. I'm just going to write this one down. You can skip past this to the next question if you don't want to see this. But I'm just going to test with the negative one here. So 5 times negative 7 over 9 minus 2, absolute value of that. So let's quickly figure that one out. So it's this times 5 and then minus 2. So that gives us negative 5.8 recurring. Absolute value of that is positive 5.8 recurring. And then we'll also test 4 times negative 7 over 9 plus 9, the absolute value of that. And let's just make sure if that works. So here, with this, we're going to times it by 4. Oops, not to the power of 4. Times it by 4. And we're going to add 9. And that gives us the same thing. 5.8 recurring. Okay, so both of these do work. Okay, fantastic. Next question. Okay, a curve has equation y equals 7 plus 4 ln 2x plus 5. Let me just write that down. Y equals 7 plus 4 ln 2x plus 5. So ln is just the natural logarithm. That's log with the base e. Find the equation of the tangent to this curve at this point, giving your answer in the form y equals mx plus c. Okay, so we need y equals mx plus c in that form. Okay, so we need the gradient. The gradient is m, right? So we can say, but m is, so the gradient of this tangent will be the same as the gradient of this curve at that point. So the gradient of a curve is the derivative of that curve. So m is equal to the gradient of this curve, the derivative. So let's differentiate. Okay, so differentiating a constant gives us 0, so that's 0. And then we've got plus 4. Differentiating ln gives us 1 over that function, 2x plus 5, multiplied by the derivative of this function. So the derivative of 2x plus 5 is 2. So let's simplify that a bit further. So the derivative, 4 times 2 is 8. So that's 8 over 2x plus 5. All right, but now we want the gradient when x is negative 2. So the gradient at that point. So we're going to say the gradient when x is negative 2 is equal to 8 over 2 times negative 2 plus 5. That gives us 8 over 1, which is 8. Okay, so that means our gradient is 8. So far we have y equals 8x plus c. And then to find the value of c, we can just substitute a point that lies on the line, that point. So let's write, we're substituting in the point negative 2 and 7. So that means y is 7 when x is negative 2. Okay, so 7 plus 16 is then 23. So that means our final equation is y equals 8x plus 23. All right, and that is our answer. Good, so basically they're just checking to see if you know that differentiating some curve gives you the gradient of that curve, and that's the same at that point. So if we had some curve, something like that, for instance, and now at this point here, well, let's do that point there. At that point there, the tangent and the curve have exactly the same gradient and coordinates. So that would be the point negative 2, 7, for example. So this gradient here is 8, and that's the point negative 2, 7. So the y-intercept somewhere here would be like 23 for the straight line. That's the basic idea. All right, let's head on to the next question. Next page, okay. So the variables x and y satisfies this equation. Let me write that down. So we've got y equals 3 to the power 2a times a to the power x, where a is a constant, the graph of ln y against x. So that means this axis is ln y and this axis is x. Okay, ln y against x is a straight line with a gradient of 0.239. So what we want to do now is convert this into the form of a straight line, the y equals mx plus c model. Okay, So let's take ln of both sides, because that's how we can get rid of the exponent parts and convert them into multiplication parts. So let's take log of both sides. So I'm going to take ln because we have specifically ln, log base e. So ln of both sides, that means ln y equals ln of 3 to the power 2a times a to the power x. And then we just apply all our logarithm laws that we know and we've studied for a couple of years already. So that means if we have two things multiplied together inside of a ln or a log, that means we can add those. So we can add the ln of both. So ln of 3 to the power 2a plus ln of a to the power x. Right, next, we also know that the exponent can move to the front. That's one of the biggest advancements that we made before calculators in order to be able to calculate really big things, is logarithms. We can thank John Napier for that. Okay, so let's move the exponent to the front, change exponentiation into multiplication, ln 3 plus x ln a. Okay, now we have it in the form of y equals mx plus c. So we've got it in the form of y equals mx plus c. So I'm just going to write it like this, plus x times m, right? Mx plus c, just to show what has to link. So these two things are basically the same. So this is the vertical axis, now that's the vertical axis, as we saw here. Right, this is our constant, no x's involved. So those are the same. X and x are the same, that's the horizontal axis in each case. And then ln a is the same as m. But we know what m is. M is our gradient here. So we're going to say our gradient, because we know that m equals ln a, but we know our gradient m is 0.239. So 0.239 equals ln a. And then we're going to rewrite this in exponential form. So we take the base of this logarithm, which is e, raise it to the power of the number that's by itself, 0.239. And that equals this value here, a. Okay, and let's kit up the calculator for that, because we have to round off to 3 significant figures. So we're going to say that's a to the power 0.239, or e to the power 0.239. That gives us 1.27. So 1.27 equals a. All right, so that is the value of a. Good. There's part B. Hence, find the value of x when y is 36. Okay, so let me copy this. We're going to use this equation here. And we know that a equals 1.27. Let me just write that down. A equals 1.27. So now y is 36. So 36 equals 3 to the power 2 times a. So 2 times 1.27 is 2.54. 2.54 times a to the power x. Okay, so I want to get this part by itself first. So I'll divide both sides by 3 to the power 2.54. So that gives us 36 over 3 to the power 2.54 equals 1.27 to the power x. And now, since we're trying to solve an unknown exponent, we want to use log of both sides again. So let's take the log of both sides. It doesn't matter which base you use for the logs. I'm just going to use normal log. So that's base 10. Log of 36 over 3 to the power 2.54 equals log of 1.27 to the power x. But we know we can move the exponent to the front, so we'll just do that. And then divide both sides by log 1.27. So that gives us log of 36 over 3.3 to the power 2.54. All of that divided by log 1.27, and that is equal to x. Okay, so again, let's just type that in the calculator. So we have the log of 36 over 3 to the power 2.54. All of that divided by log of 1.27. 3.32, corrected 3 significant figures. So 3.32 equals x. Okay, and there we go. Is there a part C? No. Next question. Question 4. Okay, show that sine 2 theta cot theta minus cos 2 theta is equivalent or identical to 1. Okay, so I'm just going to be working with the left hand side. So sine 2 theta, from our double angle identity, we know that is the same as 2 sine theta times cos theta. And then we multiply it with cot theta, which is the opposite of tan. Tan was sine over cos, so cot is cos over sine. So cos theta over sine theta minus cos 2 theta. So cos 2 theta, we've got three different ways we can rewrite that as. We can rewrite that as cos squared theta minus sine squared theta. We can rewrite it as 1 minus 2 cos squared theta, or we can rewrite it as 2 cos squared theta minus 1. So I'm going to rewrite it, since the sines here are cancelling out and we'll have a cos squared, I'm going to use the cos squared one. So I'm going to say that is the same as 2 cos squared theta minus 1. Okay, so over here, sine theta and sine theta cancels out. So if we multiply this, we get 2 cos squared theta. Here we've got minus 2 cos squared theta. And then we've got plus 1. Okay, so 2 cos squared theta minus 2 cos squared theta cancels out, and we just have 1. Okay, fantastic. So left hand side equals 1, which is identical to the right hand side. Yeah, that was quite nice. Now you could also change this into one of the other ones. Let me just, for instance, show what would have happened. So we have on the left 2 cos squared theta, and let's say we changed the cos 2 theta into 1 minus 2 sine squared theta. What would have happened if we chose that? So that would have given us 2 cos squared theta, multiplying the negative. So minus minus makes a plus, 2 sine squared theta, and then minus 1. Factor out a 2 here. We've got cos squared theta plus sine squared theta, minus 1. That gives us 2, and again, this is an identity that we need to know. Cos squared plus sine squared at the same angle is 1, and then 2 minus 1 equals 1, which again is equivalent to the right hand side. So that's a different way we could do it. And if you tried any other ways, like always, let me know in the comments below and we can have a chat about that. Question B. Okay, hence find the exact angle or exact value of this. So here we can see this is sine of 2. So basically, let me write this down. So this is basically saying sine of 2 times pi over 6. Oh, that's an ugly 6. And an ugly pi. Times cot of pi over 12, right? Oh, sorry, that's not 2 times pi over 6. That's 2 times pi over 12 is what I meant to write. 2 times pi over 12. So it's basically sine 2 theta cot theta. So sine 2 theta cot theta. So that's this part. So this part is equal to 1, and then we can move this across 1 plus cos 2 theta. So that is equal to 1 plus cos of 2 theta. And theta in this case again is pi over 12. All right, so I'm going to rewrite this in its original form just to get back to what we had. So sine pi over 6 cot pi over 12 is equal to, and now this we can just calculate. This is just a number, right? So 1 plus, and then cos pi over, I'm going to do a couple of extra things. It's just 2 marks, so we don't have to do all of this. You can just type this in your calculator basically. But cos, and then 2 times pi over 12 is pi over 6. And pi over 6, cos of pi over 6 is square root 3 over 2. Square root 3 over 2, that we also know from our spatial triangles or spatial angles. Okay, so that is what sine pi over 6 times cot pi over 12 is equal to. 1 plus root 3 over 2. Could also simplify that in some sense to have a common denominator if you like that, to make it 2 plus root 3 over 2. Same thing, but this should be fine. This will also be fine. Question C, find the smallest positive value of theta satisfying this equation. Okay, so this looks the same except that 3, I think. Minus 3 cos 2 theta equals 1. So that's the only difference. Okay, so I'm going to just start from scratch. we could also use some of the previous answers here, but let's start this one from scratch. So, or almost from scratch. I'm going to say that sine 2 theta cot theta, this part, just simplifies to 2 cos squared theta, this whole part here. Okay, 2 cos squared theta. So this part is 2 cos squared theta. And then minus 3 cos 2 theta. So cos 2 theta, again, I'm going to do the 2 cos squared theta minus 1 thing and put that equal to 1. So multiply in, that gives us 2 cos squared theta minus 6 cos squared theta plus 3 equals 1. So I'm just going to take the plus 3 over, so 1 minus 3 is negative 2. Okay, we can divide all the sides by negative 2, for instance, but let's first, I'm going to do all the steps here. So negative 4 cos squared theta equals negative 2. Divide both sides by negative 4. So that's going to give us cos squared theta equals a half. And then take the square root. So cos theta equals 1 over root 2. Plus or minus. Plus or minus. Okay, so now to solve for theta, we can say our reference angle will be arc cos of 1 over root 2. Okay, and arc cos of 1 over root 2 is pi over 4. Okay, so that's pi over 4. It's a reference angle. And now we need to check in which quadrants cos either positive or negative. So that's all the quadrants, right? But the smallest one will be the first quadrant. And since we have positive and negative, the first quadrant is one of the ones we're looking at, because that's where cos is positive. So the first quadrant will be the smallest positive value. So pi over 4, that's the first quadrant value, and that is then our answer, pi over 4. The other ones, other quadrants would be, so quadrant 2 would have a value of pi minus pi over 4. So that's going to be that. Quadrant 3 would have a value of pi plus pi over 4. And quadrant 4 would have a value of 2 pi minus pi over 4. That's 7 pi over 4. So those will be all the first values you get. Then you can go negative. If you go below this, and you can get even bigger. But this would then be the smallest positive value for which this holds. All right. Next up, question 5. Given that y equals tan squared x, show that dy dx equals this. All right. So if y equals tan squared x and dy dx, so we'll do, let me rewrite this, the y equals in this form. So that's the same as tan x squared, right? I just want to rewrite it in this way so it's easier to follow the chain rule for differentiation that we're doing. So multiply the 2 in the front, so that gives us 2 tan x to the power 1, because we subtract 1 from the exponent. And then we multiply this by the derivative of the inside, derivative of tan x. So differentiating tan x gives us sec squared x. Okay, but sec squared x, let me just rewrite this as 2 tan x, and then sec squared x is the same as 1 plus tan squared x. Another identity that's useful to know, 1 plus tan squared x. Okay, and multiplying that in, 2 tan x times 1 is 2 tan x, and then 2 tan x times tan squared x is 2 tan cubed x. And there we have it. That is what we want. Success. Okay, next, find the exact value of this. Okay, so let me rewrite that. So from pi over 4, we want to integrate up to pi over 3 this function. So tan x plus tan squared x plus tan cubed x. So here, tan x plus tan cubed x, so if we, these two together, that gives us something that we had in the previous question, except for the 2 part, right? So we can say that, so tan x plus tan cubed x. Tan cubed x dx, and then we can pull this one out by itself, so plus the integral from pi over 4 to pi over 3 of tan squared x with respect to x. Okay, so here tan x plus tan cubed x looks similar, but there's a 2 missing. So what you can say, okay, so if we multiply this whole thing by 2, we get that, but then we have to divide it by 2 again. So we can do this. Okay, so now we know this part, right? So let me just put brackets around here. Okay. So now if we differentiate the tan squared to get to this, then integrating this will give us back tan squared. So this whole part will give us tan squared x. So this is equal to half of tan squared x. Okay. From pi over 4 to pi over 3. Plus, and now we still have to integrate this, but integrating tan squared is not that straightforward. So what we can do is we can rewrite this again, tan squared, in the form, so here, we know that sec squared equals 1 plus tan squared. So let's just do this in rough work here. So let's do it in different color to show it's rough work. So sec squared equals 1 plus tan squared. So then tan squared equals sec squared minus 1. Is the same as tan squared. Okay, so we can rewrite tan squared as sec squared x minus 1. So still integrating from pi over 4 to pi over 3. But now instead of tan squared, we're going to write it as sec squared x minus 1, because that is easier to integrate. All right, let's keep this as we have it. Half tan squared x from pi over 4 to pi over 3. Plus, and now integrating this. So we know differentiating tan gives us sec squared, right? We saw here. Differentiating tan x gives us sec squared x. So sec squared x being integrated gives us back tan x. So plus tan x, and then integrating 1 gives us x. Okay, so let me take this part away here and move these things a little bit closer together, like so. And now we can say this whole part, so this whole part integrating, substituting in that from pi over 4 to pi over 3. That's what's going to give us our answer. All right, so first we substitute in pi over 3. Okay, so equals, so half times tan of pi over 3 squared. So tan of pi over 3 is, let's do this, some more rough work here. Special triangles. So if that's pi over 3, and that's pi over 6, we have these ratios. So tan of, and let's also do the pi over 4 one, since we also have pi over 4 here. So pi over 4 has these ratios, 1, 1, and square root 2. Okay, so tan of, we're substituting in pi over 3. So tan of pi over 3 is opposite over adjacent, so that's square root 3. So that's times square root 3 squared, plus tan x. So tan of pi over 3 is square root 3 minus x, and x is pi over 3. Minus, okay, now we substitute in pi over 4. So that's a half. Tan pi over 4 is 1. So half times 1 squared, plus tan x, so tan pi over 4 is 1, minus pi over 4. Okay, so we didn't need all that much space, so I'm going to continue here. And now from this, you can just type all of that in your calculator. I'm just going to do a bit of simplification, or they did find the exact value. Your calculator should give you an exact value in terms of a root thing. So I'm going to try and simplify here. So this gives us 3 over 2 for this part. So 3 over 2 plus root 3 minus pi over 3 minus, this gives us a half, plus 1, so that's 3 over 2 minus pi over 4. Yeah, let's get some common denominators. So in the left bracket, that's going to be a common denominator of 6. So that's going to be 9 plus 6 root 3 minus 2 pi. Okay, minus, and then this one, common denominator of 4. So that's just going to be 6 minus pi. So now we can cut a common denominator for both of those again. So that's going to be a common denominator of 12. It's going to be the smallest one at least. So times this by 2, that gives us 18 plus 12 root 3 minus 4 pi. And then minus 6 times 3 is 18 plus, and then pi times 3 is 3 pi. So we're almost there. Common denominator is 12. Simplify. Okay, 18 minus 18 is nothing. 12 root 3. And then minus 4 pi plus 3 pi is minus pi. Okay, so there we have it. Or if you want to split it up into two different parts, that's going to be root 3 minus a 12th pi, or pi over 12. All right, good. So this was very useful to use our previous question's answer in order to simplify this, to make it a bit quicker to solve. Oh, whole extra space. How many marks was this? 6 marks, very nice. Okay, question 6. Okay, polynomial px is defined by this. Okay, find the quotient when this function is divided by 2x plus 3 and show that the remainder is negative 6. If we only had to find the remainder, we could just substitute the solution for this factor equals 0 into this function and get our remainder, but we also have to find the quotient. So let's do the long division. So we have 4x cubed, plus 16x squared plus 9x minus 15. We divide that by 2x plus 3. Okay, so let's start. The algorithm basically goes, you start with the front part here, the first term, divided by this first part, get your answer, and then we'll see what we do from there. So 4x cubed divided by 2x is going to be 2x squared. Now we take this part of the quotient, multiply it by the whole divisor. So 2x squared times 2x is 4x cubed. And then 2x squared times 3 is 6x squared. And then we just subtract this, see what we're left with. 16x squared minus 6x squared is 10x squared. And then we bring down the next part. So you see, it's pretty much like in primary school, normal long division. We just have unknowns or x's and variables in here now. So plus 9x. Now, 10x squared, we repeat the process. So 10x squared divided by 2x, that gives us 5x. 5x times 2x is 10x squared. 5x times 3 is 15x. And then again we subtract. 10x minus 10x is nothing. 9x minus 15x, negative 6x. And then again we bring down the next part, so minus 15. And we restart the process. So negative 6x divided by 2x is negative 3. Negative 3 times 2x is negative 6x. Negative 3 times 3 is negative 9. And again we subtract. So this cancels out. Oops. And then negative 15 minus minus, so plus. Negative 15 plus 9 is negative 6. And that is our remainder. Since this has no x's, this is now a smaller exponent of x than this term, so we stop here, we can't divide any further. So this is our remainder. And here at the top, this is our quotient. So that is our quotient. Okay. So now find the integral when px is divided by 2x plus 3. Okay, so px is basically saying, so if you divide this whole px thing by this, we get that with the remainder of this. And this remainder means it's plus the remainder over the original, over the quotient. So it's you, for instance, let's just check. If we had 7 divided by 6, right? That gives us, so if, let's do the long division here again. So 7 divided by 6, and we're not going to do commas, we're going to do remainder. So 6 goes into 7 one time, so that's 1 times 6 is 6, and there's a remainder of 1, right? So a remainder of 1. So what does that mean? So 7 can be written as 6 times 1 plus 1 over 7, right? Plus the remainder over this inside part. Right? Does that make sense? plus 1 over 6, right? Because we can see here that's the same as saying common denominator is 6, so this is so 6 is the same as, well, doesn't really matter, but you can see this is what happens. So in here, if we divide this by this, we get the quotient, which is 2x squared plus 5x minus 3, plus the remainder over 2x plus 3. So the remainder is negative 6 over 2x plus 3, right? So that is the idea here. Now I'm just going to rewrite it slightly. So 2x squared plus 5x minus 3, but then I'm going to rewrite this as negative 6 times 1 over 2x plus 3. Okay, the reason for that is so now we can just integrate all these parts separately. Let me just put a bracket around to make sure it's mathematically accurate here what we're doing. Okay, so we can integrate all of these parts separately. So integrating this, we add 1 to the exponent divided by the new exponent, plus, and again add 1 to the exponent divided by the new exponent, same here, and then minus 6. But now I rewrote this in the form so we can see this. If we integrate this, we get ln of 2x plus 3, but divided by the derivative of the inside part. So if we differentiate 2x plus 3, we get 2. And remember, usually we want to add a plus some constant. And then let's just simplify this a bit. Well, there's not much to simplify. Only thing we can simplify is this division part here. So we have 2x cubed over 3 cubed over 3 plus 5x squared over 2 minus 3x and minus 3 ln 2x plus 3 plus some constant. All right, good. Now p of x plus 6. Okay, so this plus 6 should give us a clue here. So p of x has a remainder of negative 6. So if we just add 6 to this, right, so if we said p of x plus 6, then we would have no remainder. We would have no remainder. So that would just be this times that, right? The quotient times the divisor, if we had a plus 6 here, because that would cancel out the remainder. So that means p of x plus 6, so let me do this, p of x plus 6 equals this whole thing. So 2x plus 3 times 2x squared plus 5x minus 3, right? That's it. That's the p of x plus 6. Okay, so if we want to solve this equation now, p of x plus 6 equals 0. So we're going to say this whole thing, so 2x plus 3, but this part we can still factorize further. So let's make our two brackets for that, equals 0. So this would be a x and a 2x, and it's going to be 2x plus 3 there, and then x minus 1 here. Yeah, that's going to give us 5x. Good. Okay, so we need to solve each of these, but for when x equals that. So a couple of ways. You can first rewrite this in terms of the cosec thing. So it doesn't really matter. Let's do that just to show this is exactly what happens. Or you could first solve for x and then just say, but that answer equals this. That's probably what most people would do. I'm just going to replace it with the cosec thing. So 2 cosec 2 theta plus 3. Okay, so that's from this first bracket, times just times cosec 2 theta plus 3, and 2 cosec 2 theta minus 1 equals 0. Okay, so from this one, we'll get cosec 2 theta equals negative 3 over 2. The cosec 2 theta equals negative 3 over 2. from this one we'll get cosec 2 theta equals -3, and from this one we'll get cosec 2 theta equals 1/2. Okay, but since we don't have arc cosec on our calculators, we'll have to convert this into sine, tan, or cosine. So cosec is the same as 1 over sine. So basically, if you just flip this around, we'll get sine 2 theta equals, and then we flip this one around as well, -2 over 3. Here, we'll flip this one around to get sine 2 theta, flip this one around to get -1 over 3, and again this one, flip it around to get sine 2 theta equals, and then flip this one around too. Okay, so let's solve each of these. So this means our reference angle here is going to be arc sine of 2 over 3, which is, so arc sine of 2 over 3, 41. Are we working in degrees? Yes. So 41.81. 41. I suppose we could. I'm going to do this. In the end, we want three significant figures, or 1 for angles. But we could use a bit more accuracy in the meantime, and then our final answer just round off to one decimal place. That should be good. Okay, so that's our reference angle there, which means that 2 theta, so we had a negative value for sine. So sine, again, is negative in these two quadrants, in 180 plus and in 360 minus. So in our third quadrant, we'll have that 2 theta equals 180 plus this. So that's going to be 221.81. Again, we don't need the general solution because we're just working between 0 and 135 degrees. So that's just going to be in the first rotation, basically. But you could add, for a general solution, it would be nice if you added plus k times 360, where k is an integer, and then simplify from there and find your final solutions from all the general solutions. But this should be fine for the first rotation. And this means then that theta will be equal to, divide that by 2, so 221.81 divided by 2 is 110.9. So 110.9 degrees. Okay? That's right? Yeah. 0.91, but 9 is fine. So that's one solution so far. Okay? We also have the fourth quadrant, so 360 minus. So 2 theta is equal to 360 minus 41.81. 360 minus 41.81 is 318.19. So 318.19, divide that by 2. Divide that by 2, we get 159.1. So 159.1. Again, that's too big. That's not between 0 and 135. So far this one, underlined one, still is fine. Here we have our reference angle is then arc sine of 1 over 3, which gives us, so the arc sine of 1 over 3, oops, 19.47. So that's 19.47 degrees. So again, it's negative. So we're going to be working in, again, these same two quadrants, 180 plus and 360 minus. So 2 theta equals 180 plus, so that's 199.47, which means that theta equals that divided by 2. So 199.47 divided by 2, 99.73. So 99.74 or something. Doesn't really matter too much. So that is fine. That's between 0 and 135. And then we could also check the fourth quadrant. 2 theta is then 360 minus our 41.81. Oops, 41.81. And we divide that again by 2. So 318.19. Not 41, sorry. 360 minus, what did we have here? 19.47. 19.47. We have that, we divide that by 2, So 340.53 and then 170. So 340.53 gives us theta is then 170.26-ish. Okay. So again, this is the only one that works here. And then this one, no real solutions. Right? If you remember on your graph, sine graph only goes up to 1 maximum and -1 minimum. So it's impossible to have sine value equals 2. And you should get an error if you try. Let's see, arc sine of 2. Yeah, undefined for values outside of -1, 1. Alright, so these are our only two solutions then. Theta, let's just draw a slightly better theta. So theta equals 99.7 or 110.9. Those are the only values between 0 and 135 for which this is true. All right. Next up, question 7. A curve has this equation. Okay, let me write down that equation. E to the power 2x, 2x times y, minus e to the power y equals 100. Okay, we have to show that the derivative with respect to x equals this. So here we are going to have to do implicit differentiation, or at least that's what I would do. Definitely the easiest way to do this, because it's much more difficult to separate out the y's, I think, by themselves. But you can also, if you gave that a go, let me know in the comments how you did that, and let's compare the answers. Okay, so this part will be a product rule here. So the product rule will be differentiate, or keep the first one, so e to the power 2x, and then differentiate the second part. So differentiate this, so differentiating y with respect to y is 1 times dy dx. So every time you differentiate a y part with respect to y, write dy dx with it, with respect to x. Because it's implied, that's where the term implicit differentiation comes from. It's implied that y is a function of x, right? Okay, plus, so that was keep the first, differentiate the second, and then we do it the other way around for the product rule. Keep the second one and differentiate the first one. So differentiating e to the power 2x gives us e to the power 2x times the derivative of that, which is 2. And then minus differentiating this is just e to the power y times dy dx. dy dx. Okay, because it's this multiplied with the derivative of that part. And the derivative of y is 1 times dy dx. Okay, equals, and then if we differentiate 100, a constant, we get 0. Let's factor out the dy dx. dy dx. And what's left here is e to the 2x minus e to the y equals, and then let's take this term across. So that's going to be negative 2e to the 2x y. All right, and then we can divide by this part. So dy dx equals negative 2e to the 2x y over e to the 2x minus e to the y. Is that what they were looking for? Almost. So they just switched the negative. So just to show you again, if we've got a over b, let's say we've got negative a over b. That's the same as a over negative b, and that's the same as negative a over b. So each of those is correct. Basically what we're doing here is now we're just switching the negative from the top to the bottom. So dy dx equals, so take the negative away from the top, or multiply both top and bottom by -1. That's another way to think about it. So 2e to the 2x times y over, and now the negative e to the y becomes positive e to the y, and e to the 2x becomes negative e to the 2x. And there we have it. That is it. Now show the curve has no stationary points. Okay, so let me again just copy the function, and let's copy also the derivative. Okay, so we have to show that there's no stationary points. So a stationary point would happen when the derivative is 0, when the gradient is 0, right? So that's what happened when this top part is 0. So we can see, okay, we're going to do this by contradiction. We're going to try to find a stationary point and then see that that does not suffice, or does not satisfy anything. So if this top part were to be 0, 2e to the 2x times y, if that were to be equal to 0, that would be the values for y and x where there would be a stationary point. Okay, so divide both sides by 2, so that gives us e to the 2x is then equal, or e to the 2x times y is then equal to 0. So that means either e to the 2x equals 0 or y equals 0. Now this part, this is not possible, right? It's not possible because any positive number, like e for instance, raised to any exponent can never be 0. So this is not possible. Now our other option is that y is 0. So let's check what happens if we try to make y 0. So e to the 2x times 0 minus e to the 0 must be equal to 100. So anything times 0 is 0. So and e to the 0 is 1. So negative 1 equals 100. That's obviously silly. That does not work. So therefore, by contradiction, we've shown that it has no stationary points, because neither this cannot be 0 and y can also not be 0 in order to make any sense. All right. Question C. It is now required to find the x-coordinate of P, which is the point on the curve at which a tangent is parallel to the y-axis. Okay, so parallel to the y-axis. So what would be the gradient of a line parallel to the y-axis? It would be an undefined gradient, right? An undefined gradient. So this is our gradient. So where is this undefined? Well, it's undefined when we divide by 0. But before we get there, let me again just fetch our original, let's fetch our original equation, original curve. Okay, so vertical line, undefined gradient. So that means this bottom part must be 0 for it to be undefined. So e to the power y minus e to the power 2x must be 0 in order for the gradient to be undefined. So that gives us e to the y must be equal to e to the power 2x. Now since our base numbers are the same, that means our exponents are also equal. So y equals 2x. Then we can substitute that into our equation here. Okay, so e to the power 2x times y, but y is 2x, minus e to the power 2x, which is y, equals 100. Okay, let's factor out e to the 2x. So e to the 2x leaves us with 2x minus 1 equals 100. Okay, that looks promising. We've got the 2x minus 1 thing here. Now we need some lins. So let's take ln of both sides. Okay, so I'm going to again move this over here. Okay, let's move this whole thing over here. Give us some more space in case we need it on the right hand side. And let's get rid of this. Okay, where am I now? Oh, that seems fine. Okay, so let's take ln of both sides. So ln of e to the 2x times 2x minus 1 equals ln 100. Okay, now we can split this up into ln e to the 2x plus ln 2x minus 1 equals ln 100. All right. Then here, what do we want? So let's move this exponent to the front. So 2x ln e plus ln 2x minus 1 equals ln 100. All right, so ln e is just 1, so we can cancel that out. So let's keep the 2x by itself. So 2x equals, and then we've got ln 100 minus ln 2x minus 1, and divide by 2. So x equals a half of ln 100, just write a better half of ln 100 minus half of ln 2x minus 1. Okay, that's looking pretty good so far. Minus half ln 2x minus 1. And now basically just one more step. I'll do it in 2 for this one. So here we can say let's move the exponent back as the coefficient back to an exponent. Leave this one as it is because that's already correct. And then finally that gives us 100 to the power half is 10. So ln 10 minus a half ln and then 2x minus 1. Alright, so basically what we needed to know is that a vertical line has an undefined gradient, which means it has a denominator of 0, and then substitute that back into our equation, take ln of both sides and simplify. Now question D, and that's our final question. Okay, use an iterative formula based on the equation in part C, because that's basically just this whole equation, so I'm just going to use this one. Basically just that. Okay, so I'm just going to rename this xn plus 1 is when this is xn. Okay, so each next term, etc. We want to start, we need to get to a correct answer of 3 significant figures in the end, use an initial value of 2 and give each iteration to 5. Okay, so initial value of 2, so I'm going to say x0 equals 2. Then x1 is going to be ln 10 minus a half ln 2 times, and then it's going to be 2 x0 minus 1. Okay, and that gives us, okay, so I'm going to need to type this whole thing in one time at least. So ln 10 minus a half times ln 2 times our other value, in this case it was a 2, minus 1. Okay, 1.7533. So 1.7533, correct to 5 decimal places. And then we'll do x2. So x2 is now when we substitute this in. So I'm just going to take this, substitute in our previous value, 1.7533. That's 1.8431. So 1.8431. Then x3, the next one. So we're going to keep going until the third significant figure rounds off to the same value each time. Okay, so here we're going to add 1.8431. 8431. So 1.8085. 1.8085. x4. Then this is 1.8085. 1.8216. 1.8216. Let's go here, continue with x5. 1.8216. 1.8166. 1.8166. x6. So we've got 8281. It rounds off to the same thing, but let's keep going a little bit just to make sure. 1.8166. 1.8185. 1.8185. Okay, so this looks good. Looks like it rounds to 1.82 for 3 in a row already, both above and below. Let's just do another one to make sure. So 1.8185. Whoa. 1.8178. 1.8178. So yeah, again it rounds to 1.82. So we can say x is 1.82. All right. So I believe that's it. That is it. So again, if you have any other questions, let me know about it. If you did something in a different way and you want to check if that makes sense, let's discuss in the comments below. And hopefully this was useful. So again, in the comments, not in the comments, in the description below, there will be links to the website containing all these past papers. Again, this one was from March, February this year, Pure Math Paper 2. And there's past papers from all the way back in 2001 up until this year. So lots of ones to go through, and I'll try to get through all of them in the next couple of months, hopefully. All right, and if you also have a different system, instead of Cambridge, if you've got a different syllabus or curriculum that you may have some interesting questions or past papers on, let me know, and I can try and go through some of those as well. All right, and yeah, that's it. Hope to see you in the next video.